In northern lands, the cycle of the seasons was marked by standing stones and by observing the horizon. The point where the sun rises shifts every day. But twice a year, it stands still. These times were recognized as midsummer and midwinter. When it moves again, the season begins to change. The world over, the movement of the sun was a calendar. In this Native American cave, when an arrow of sunlight strikes this spot on the wall, it's midwinter. Chichen Itza in Mexico, a Mayan city steeped in astronomy and religion. A citadel and observatory. A place of sacrifice. Here, offerings were made to the gods to ensure the rains returned. A special monument, the Castillo, and, at the equinoxes, the shadow of a god in the shape of a rattlesnake, a serpent of sunlight on a stairway from heaven. They didn't know it, but ancient observers were recording how Earth's orbit of the sun causes the seasons. That orbit is called a year. Each day, due to the tilt of Earth's axis, the angle at which sunlight strikes us changes slightly. Over a season, it changes a lot. In the 6 months from winter to summer, the change is greatest of all. From this position, it's summer in the northern hemisphere. The north has short nights and long days. At the equator, it hardly changes. The south has long nights and short days. From this opposing position, it's winter in the northern hemisphere. Short days and long nights in the north, the long days and short nights of summer in the south. Our ancestors had a clearer view of the cosmos than we do. From city and suburb, the stars are fogged by lights and pollution. Nowadays, vistas like this are glimpsed only in the remotest places. In days of old, everyone saw the sky and knew the sky. They wouldn't miss the lights of the aurora, or a new star, a nova, the sign of birth. Or a comet, a heavenly courier. Some astronomers suggest it was a comet that led the wise men to Bethlehem. Would they even see a comet today? Shooting stars were once a nightly show. To the Egyptians, there were messages from the gods. When a meteorite fell out of the sky, they set it on a plinth and called it the Stone of Heaven. The ancients watched the heavens the way we watch soap operas. The sky was a panoramic screen full of characters and beasts, a way to make sense of the stars. They helped shape the legends of mythology we know to this day.
Wonders of the Universe will continue on TLC. Wonders of the Universe continues on TLC.
Our star maps have changed, But myth persists. The names of antiquity are the constellations of modern astronomy. But how did they reach us? For they had origins in different places, in different cultures. Somehow, somewhere, the names of the constellations were codified. There's a theory it was the work of a lost civilization, a people dispersed more than 3,000 years ago after a volcanic disaster. They lived in the Aegean, on an island in the eastern Mediterranean known today as Thera, or Santorini. They were traders and navigators. Archaeologists have unearthed a wealth of artifacts and a seaport dating from 1450 BC. And there's evidence, some astronomers say, that star maps were made here, charts that name the constellations as we know them today. Perhaps those ancient observers on Santorini fed the legend of Atlantis, learned astronomers in flight from catastrophe. How high the moon, how far the stars. Around the world, astronomers pursue an age-old quest. They're down-to-earth people, scientists who understand the insignificance of our planet in the grand scheme of things. Since the time of the ancient Egyptians, the skies have scarcely changed. And the questions are the same. Will we ever reach those stars? How vast are the heavens? Questions that take us to the edge of time. In the quest to put a yardstick across the universe, the moon is our first measure. The moon is our only natural satellite. It's 250,000 miles away, and its light takes only a second to reach us. The Earth is one of 9 planets that orbit the Sun. The Sun is 93 million miles away, and its light takes over 8 minutes to reach us. From the outer planets, the Sun is just a brilliant star. Neptune is 3 billion miles from its warmth. Sunlight takes 4.5 hours to arrive here. Beyond the planets are the stars, but to the naked eye, they look the same, two-dimensional. Now, thanks to astronomy, we know much of their nature and their distance. Among these stars, if you don't count the Sun, is our nearest star, Alpha Centauri. It's the big one to the left. Alpha Centauri is 25 trillion miles from Earth. Alpha Centauri is more than one star. Indeed, it's more than two. It's a triplet. Their light takes almost 4 1/3 years to reach us. Or, as astronomers would put it, Alpha Centauri is 4.3 light years from Earth. Out here, at such a distance, the Sun is a dot, a modest star visible to the naked eye. Onward and outward, and some 200 light years from home, the stars of W Ursa Majoris, twins that exchange material. Farther, and through the stars of Orion. From Earth, they're a two-dimensional pattern. Out here, we realize they lie at different distances. They have depth. We've reached 1,500 light years, and the heart of the constellation, the Orion Nebula. It's a great cloud of dust and hydrogen, a cocoon of gestation, a place where stars are born. If we kept traveling onward at the speed of light, it would take another 30,000 years to reach the center of our galaxy. Instead, we leave it. We journey to a vantage point outside, where we look back at our galaxy, a spiral of 200 billion stars, the Milky Way. But it's just one in a local group of galaxies. That group, in turn, is part of a bigger group, a supercluster. Superclusters form webs, networks that cross the universe, the voids between seemingly empty of galaxies. But there's more to the cosmos than meets the eye. Over 90% of its mass is invisible. It's called dark matter, a sea of exotic particles that possibly fills the universe.
Wonders of the Universe will continue on TLC. Wonders of the Universe continues on TLC.
The Milky Way is big. A beam traveling at the speed of light at 186,000 miles a second takes 100,000 years to cross our galaxy. At the same speed, a journey through our solar system is a matter of hours. How do astronomers know all this? How did they learn to measure the universe? The story begins over 2,000 years ago in Egypt. It involves basic geometry, calculations familiar to temple builders. It gave the world the first unit of astronomical measurement, a unit as big as the world. The reflection of the sun shining directly down a well in Aswan. 500 miles to the north, in Alexandria, a column cast a shadow. It was noon in both places, so why the difference? According to legend, a librarian called Eratosthenes realized it was due to the curvature of the Earth. When the sun was directly overhead in Aswan, it was at an angle in Alexandria. That caused the shadow. The difference in angle was a 50th of a circle, so the distance between Aswan and Alexandria must also be a 50th of something. a 50th of the circumference of the Earth. That's geometry. And that was Eratosthenes' reasoning. He was right. The Earth's circumference is about 25,000 miles. 200 BC, and it was known that Earth was an orb in space. Where it lay in space was tougher. A Greek idea put the Earth at the center of things. Around it, set in a series of crystal spheres, orbited the moon, the sun, the planets, and the stars. But the planets were a puzzle. They were called wandering stars. Their progress through the heavens could be erratic. Some would stop, reverse, and proceed again. The Greek astronomer Ptolemy had an answer. He accounted for their wanderings with epicycles, little orbits made by the planets around their main orbital paths. It's a clumsy idea, but it seemed to fit the observations. It seems to work for planets like Venus and Mercury, which speed across the sky at twilight. But it fails with others, like Mars. For 1,400 years, there was no progress. Then, an eagle-eyed Dane named Tycho Brahe had half a good idea. He still had the sun going around the Earth, but he had the planets going around the sun. The passage of a comet sparked his theory. Observing the great comet of 1577, Brahe calculated that in one night, its movement against the background stars was much less than the moon's. This put comets among the planets, smashing the notion of crystal spheres. But Brahe still had Earth at the center of the universe. The Polish astronomer and cleric Nicholas Copernicus had already knocked down that one. He put Earth in its place as a planet orbiting the sun. But he assumed that the orbits of the planets were circles, and he couldn't explain the eccentric loops of Mars. A German mathematician, Johann Kepler, could. He worked out that the orbits of the planets aren't circles, but ellipses, and that the speed of the planets depends on their distance from the sun. The picture of the solar system was complete. Enter the English scientist Isaac Newton. Newton explained more about orbits with his famous theory of gravity. He imagined a cannonball fired from a mountaintop. Fire it faster, and it goes farther. Fire it fast enough, and it goes into orbit. It becomes a satellite, like the moon around the Earth. Or the many moons that orbit Jupiter. Newton's genius was to recognize that the force that makes a cannonball fall to Earth is the same force that governs the motions of moons and planets. It's the force that dictates the speed of orbits. In the solar system, the closer a planet is to the sun, the faster it must move to stay in orbit. And it's the force that boosts spacecraft as they explore the planets.
Wonders of the Universe will continue on TLC. Wonders of the Universe continues on TLC.
At the dawn of modern astronomy, there was a map of the solar system, but it was a map without a scale. The dot is Venus crossing the face of the Sun. It happens when the orbit of Venus carries it through our view of the Sun. Seen from two different places on Earth, Venus makes two different tracks across the Sun. That difference is the key to the planet's distance from Earth. Simple trigonometry gave astronomers the answer, and that answer provided a scale for the solar system. But how to measure the stars? As our planet circles the Sun, we'd expect the nearer stars to move from side to side as our perspective of the cosmos changes. Astronomers looked in vain for the effect, but a Dane called Ole Romer found another effect of the Earth's orbit of the Sun. He was observing eclipses of Jupiter's moons. They came sooner than expected, he discovered, when the Earth and Jupiter were on the same side of the Sun in their orbital paths. The eclipses came late when Earth and Jupiter were on opposite sides and farthest apart. The reason was the time taken by light to travel from Jupiter to Earth. Thus, Romer showed that the speed of light was measurable, not infinite. But the puzzle remained. How could the distance to the stars be measured? As telescopes became larger, more and more stars sprang into view. In the 18th century, with the huge telescope he built, English astronomer William Herschel began to map the heavens. Painstakingly, he counted the stars. There were thousands. He produced a chart of how he thought they were arranged and put the Sun near the center. Herschel thought this was all there was of the universe. Evidence that there was more came from Birr Castle in Ireland, where the 3rd Earl of Ross built an even bigger telescope. It was the mid-19th century, and Ross had discerned faint, wispy clouds. He drew them. Within some clouds were swirling structures. Beyond the Milky Way, Ross had glimpsed mysteries. Astronomers were finally coming to grips with the distance of stars. New, precise observations revealed that stars do shift position as the Earth orbits the Sun. It's hard to see because they're so far away. The effect is called parallax. It's measured by observing a star from one side of our solar orbit, then 6 months later from the other. How far the star shifts depends on its distance. The closer the star, the more it shifts. Astronomers found that stars are incredibly distant, light years away.
Wonders of the Universe will continue on TLC. Wonders of the Universe continues on TLC.
From the depths of the cosmos, a star that beats like a heart. It's called a Cepheid. Astronomers can tell its distance from the rate of its pulse. Cepheids are celestial beacons that help measure some of the most distant objects in the sky. Cepheids beat in globular clusters, collections of stars that hover outside the main disk of our galaxy. By measuring the pulse of a Cepheid within, the distance of the cluster can be worked out. Globular clusters are too remote to measure by the parallax method. The observation of Cepheids has helped map the structure of the galaxy. The Sun isn't at the center, but 2/3 of the way to the edge. At last, the sun was dethroned from its place at the hub of the universe. But there was another surprise. Observers have seen it since ancient times. It's a fuzzy patch in the constellation of Andromeda. Near or far, no one could tell. Then, in 1923, the American astronomer Edwin Hubble discovered Cepheids in its outer reaches, so faint they were far beyond the stars of our own galaxy. Hubble was looking at another galaxy, more than 2 million light-years away. As Hubble peered deeper into space, he found more and more galaxies of every shape and size. Hubble unveiled an expanding universe. Galaxies traveled outward in all directions. The farther away they were, the faster they appeared to recede. The evidence was in their light. It shifted toward the red end of the spectrum, a sign of lengthening wavelengths. The wavelengths were stretching because the space between the galaxies was stretching. The galaxies were relentlessly moving apart. Edwin Hubble had stumbled on a clue to the origin of the universe, the Big Bang. His brilliant observations revealed an ever-expanding universe, a universe that must have a starting point, a moment when time and space began. Today, in towers of astronomy, the quest to measure the universe goes on, but our instruments are crude. Observations by the world's most powerful optical telescopes have a 30% margin of error. We need finer devices. Like the satellite Hipparcos, clear of atmospheric distortion, it surveys the nearest stars, measuring distance as never before. Another is the Hubble Space Telescope, continuing the work of Edwin Hubble himself. In 1994, it studied Cepheids in a galaxy too distant for telescopes on Earth. Its observations put astronomy in a spin. The Cepheid set the distance of the galaxy at 50 million light-years. That distance, when linked with the galaxy's redshift, told astronomers that the universe was only 9 or 10 billion years old. If the universe is so young, how is it that stars much older have been measured? Are the winking Cepheids sending false signals? These Cepheid readings are probably right. It might take years to see them in context. Our picture of the Big Bang could well be all wrong. Indeed, was there even a Big Bang? And if there wasn't, why does the universe expand? These are the questions scientists confront as they tiptoe toward the edge of time. In years to come, our ideas of the cosmos may be as quaint as those of ancient observers.